Okay, so since we started looking at limits with infinity, in relation to vertical asymptotes, the limit of a function as x approaches vertical asymptote would have typically an answer with either positive infinity or negative infinity. Then we looked at horizontal asymptotes, and those are problems where the limit of our function as x approaches positive infinity or negative infinity would equal the value b, where b equals y is your horizontal asymptote, okay, in most cases. So now we're getting to look at limits with infinity in the same way that would be asked of functions, and it would correspond to the horizontal asymptote. Here we're using it with the properties of limits, and it's not always the horizontal asymptote that we need to know. Sometimes it's still like the limit of a constant that we need to look at. So here we go. This is one that we kind of saw the other day as an example. You need to know that this is true. The limit of sine of x over x as x approaches positive infinity is 0, and also the limit of sine of x over x as x approaches negative infinity is 0, because it's going to help us when we use our properties. So you may remember the properties. We take the limit of our numerator and the limit of our denominator, but in this case, we can actually simplify this rational function as the limit of 5 plus sine of x over x. So now, in this particular case, we can use the product rule. I'm sorry, not the product. The sum rule. Take the limit of 5. Okay, as x approaches infinity, and so plus the limit of sine of x over x as x approaches infinity. So, like I said, this we know to be 0, and this right here is 5. Just as x approaches any a, like 2 or 7, the answer would still be 5. As x approaches positive infinity or negative infinity, it would still be an answer of 5. So this gives us our limit answer. I'm going to box that off. So a very simple one where we use the properties, okay? And now we end up using the properties to justify an answer for other limit problems. So before we get to that, I'm going to go over something else with you. Okay, so I apologize that these slides are pretty crooked. I did not take a good snapshot of my slides today, but I think you can still see it and copy down notes. So the limit of c over x to the r power as x approaches infinity is 0. Okay, that means that we do have a rational function, but our numerator is some constant, and the denominator is x to some power, but it's got to be like 1 or 2 or 3. It's got to be positive, and it has to be a rational number. And same goes for when it's the limit of this expression as x approaches negative infinity, it is also 0, okay? All right, so the x is less than 0s because x is approaching negative infinity. So there are 2 examples of that. So it doesn't matter if c is 1 or it's 6, it still works kind of the same way, it's your constant. I'm showing it with x approaches negative infinity because it doesn't matter if it's negative or positive. And we know that from the first one because it is our common function, y equals 1 over x, and you can sketch that without a graphing calculator, and you know what that looks like. The x-axis is also your horizontal asymptote, and your y-axis is also your vertical asymptote. So as x approaches negative infinity or positive infinity, the answer is 0. And this may not be a common function, this is 1 over x squared, but it takes on the same type of look to its graph. and this is a horizontal asymptote, this is a vertical asymptote, and we're sketching its graph anyway. So I'm going to make that a 6. It looks like this. So as x approaches negative infinity or positive infinity, it is also 0. So this is always true, and that is a definition we're going to use with our properties. Okay, so perhaps we're looking at this function, and you may not know the graph when x is 0, but you remember the leading coefficient test, you have some sort of idea as to what the answer is, okay? But we're going to use that definition we just went over in the properties of limits in order to find this limit, like prove that it is going to be, well, the answer we're going to write. So here we go. When we went over the properties of limits, I did one where you factored out x to some power. And we did that just, so we can simplify and get our answer quicker. But here we actually need to do that to find the limit. So I'm going to factor out the highest degree. Okay, I'm going to factor out x to the 4th power. And that leaves me with 2 minus 1 over x squared minus 8 over x cubed. So now I'm going to do the limit properties. Perhaps you're going to need more steps than I'm going to show you, and perhaps you know how to do this in one step like I do. If you are unsure of how I'm doing this, then please review that lesson. So taking the limit of the factors and the limits of each term. So essentially we're using our product rule and our difference rule. Okay, so the first one, if you have a very large value, you raise it to the 4th power, you're still going to get positive infinity. Okay, over here we just went over the limit of a constant as x approaches negative infinity or positive infinity. And these are our definitions where they become 0. So essentially we have 2 times infinity. Okay, and that is infinity. That is our answer. Okay, so sometimes it's not coming out to an answer like 5, and sometimes we need to write down infinity or negative infinity. Okay, so I'm going to give you some practice, and good luck. I think you'll be ready. Because this kind of introduces the end behavior model, and as we get through it slowly and slowly, more of that will make sense to you. And our unit is not at an end yet, but we're getting towards it. So congratulations, and again, good luck on the practice.